somewhat often a strange proposition because it's very difficult to conceive. Okay? Shortly after he predicted this on a theoretical basis, in 1927, an experiment was done with particles, and it was proved that particles can actually exhibit wave-like properties or can behave as waves. How can they prove that? They have shown that if you have electrons, a beam of electrons, they can diffract. They can see diffraction patterns. And you know that diffraction patterns only show up with waves. So if you have a beam of electrons and you see a diffraction pattern, then that means you have waves. And the experiment is very simple. You can just have a slit like this, an opening, and then you have a fluorescent screen, a very sensitive screen here at the back. And then you have all the electron beam, very high density, high intensity electron beam coming through, okay, going through here, the slit, and then hitting the fluorescent screen back here. Now, if electrons are simply particles, the particles are directed in this direction, so they will be directed in this direction, and they will be incident in an area here exactly equal to the area of the slit, of the opening. Okay? And you will only see an image in this area. But in this experiment, they have shown that particles, electrons, are actually seen, or an image is seen in a very larger area, much larger than the opening or the slit. So that means there is diffraction. Okay? And diffraction is only true for waves, right? It's not the case for particles, unless the particles behave in a wave-like manner. Okay? And so this experiment established the proposition by de Broglie in 1924. So de Broglie also said the following. He said, if we have a particle of mass m, therefore, and moving with a velocity v, then the magnitude of its momentum is m times v. That is from our classical mechanics, right? So de Broglie said, if that's the momentum for a particle of mass m moving with a velocity v, then the wavelength of the wave associated, the wave of this particle, is equal to Planck's constant h divided by the momentum. So he actually went ahead and made up a theory as how you get the wavelengths of the moving particle. It's simply Planck's constant over p, which is h over mv. That's p. Okay? Now, what we can do here is writing p according to de Broglie is equal to h over lambda. Okay, according to de Broglie's theory. Or we can have it equal to h bar, which is the reduced Planck's constant, which is h over 2 pi. So we can make it h bar times 2 pi. So h is equal to h bar times 2 pi, and then we divide that by lambda. So that's another way. So 2 pi by lambda, we call it k. And k is called the wave number. K is a wave number. And this wave number is an important number because immediately if we multiply the wave number by h bar, or reduced Planck's constant, we get the momentum of the particle. So It's immediately the momentum is h bar times k, where k is the reduced wave, where k is a wave number. And remember, k is simply 2 pi by lambda. Lambda is the length, right? So 2 pi is just a number. So k is given in meters minus 1, length minus 1, or angstrom minus 1. And k is a wave number. Okay, so then the immediate question comes, okay, what's my wave? What's your wave when you move? Are you really a wave when you're moving? Have you seen a car moving and it behaves like a wave? Or have you seen a train moving and it behaves like a wave? Or have you seen a friend of yours walking and he behaves like a wave? Obviously, you haven't seen that. So how can we believe this? How can we consider this as right? Of course, one of the things is this experiment here. But this is done for electrons, not for humans. Okay? So what's the idea? The idea is we all have waves associated with us. Cars have waves, trains have waves, but the problem is these waves are very small. And you don't see them, you don't observe them. They're too small compared to the size, my size, your size, the car size. So if you have somebody this big, okay, moving, a car or a train, and you have a wave this big, wavelengths, this big here, then the wavelength and the extent of the wave is so small compared to the size of the object. So you can't see the wave. You can't feel the wave, right? But if you have a wave which is so large compared to the object, like an electron, then you actually observe the wave. The electron is very, very small. The dimension of the electron is in picometer, 10 to minus 12 of a meter. And the wave associated with moving electrons is angstroms. So it is 2 orders of magnitude larger, 100 times larger than the electron. So it dominates the electron. So when the electron moves, you only see the wave, or spectroscopy only sees the wave of the electron. You don't see the electron. But when you move, your wave is so small, angstroms in length, but you are meters in length, or the car are meters, hundreds of meters, the train is hundreds of meters. So their waves is angstroms, so you don't see it. Okay? So if we have particles, if you have electromagnetic radiation, we see that, as the frequency increases, we go to higher and higher photon energy. Similarly, if you have particles, okay, for particles with their waves have higher and higher frequencies, then the particles have more and more energies, okay, and their wavelengths increase. If we have their wavelengths going down, right, that means their energy increase too. Let's look at this example. This is a very interesting example. Find the de Broglie wavelength of 100-gram billiard ball. We know that the billiard ball is probably this big. Probably, the dimensions of the billiard ball, something of the order of 10 centimeters, the diameter, say. Okay, 10 or 5 centimeters. So this is the billiard ball. The weight is 100 grams. That's a typical billiard ball weight. And it moves with a velocity of 0.5 meters per second. 0.5 meters per second, that's a very high velocity, because that is 0.5 times 60 times 60 okay? And that will be something like 3600, okay, times 5 times 0.5, okay? So 3600 times 0.5, you get something like 1 8, right? 553 uh, 18, and then you get something uh, like something like this. I think 1800 meter per second per meter per hour, okay, or 18,000 meter per hour. I think, yeah, 18,000 meter per hour, which is 18 kilometers per hour. So that's the kind of velocity maybe we're looking at here. Okay, so let's see what wavelengths can we associate with this billiard ball. So P equals m times v. So this is m in kilograms, okay, 0.1 kilogram. This is the velocity in meters per second. So the momentum is 0.05 kilogram meter per second. De Broglie's wave lambda is h over p. So this is h here, and this is p. So what do we get for de Broglie's wavelength? 1.3 times 10 to minus 32. Can you imagine 10 to minus 32 of a meter, right? So what we are saying is this billiard ball has a wave associated with it, but the wavelength is this much. So can you compare this wavelength with the size of the billiard ball? It is 10 to power 32 times smaller than the size of the billiard ball. Would you be able to see this at all? Of course not. And you can imagine, if you go bigger with somebody, if you walk, we don't walk for 80 kilometers an hour. We walk at much lower velocities. So we even have smaller wavelengths. And look at our size. You cannot observe our size. Okay? So the billiard ball is, an example, and it just shows you for this small object how small is wavelength. And that is why we don't see the wave nature of objects when they move, big objects. But when we look at small objects, we see the wave nature, electrons, protons, etc. And remember one thing, in electrical engineering or in electrical applications of materials, you deal with very small object particles that are electrons. This is very different from other engineering disciplines like mechanical engineering, like even civil engineering, where they deal with large objects, machines, cars, vehicles, aeroplanes, etc. So they don't need to think about the wave nature of particles. They can only talk about the particle nature or the object nature of particles. But for people dealing with electrons, like electrical engineers, like physicists, who do experiments with electrons, they have to bring into play the wave nature of particles. Okay? So, that leads us to a fundamental question then. We know in classical mechanics, we have these three laws of Newton. And in dynamics in particular, we have the second law, which simply says force is equal to mass times acceleration. And that second law, in classical mechanics, deals with objects, with particles. Okay? And it works very well for large particles, works very well for cars, human beings, uh, trains, aeroplanes, etc. But clearly, if we want to look at the wave properties or use the wave properties of particles, we cannot use Newton's second law. It doesn't work. It should not work for electrons. We can use it as an approximation, to study electrons' motion on dynamics. But we know that it's more appropriate to look at electron motion as wave motion. So we should come up with what we call a dynamics or a mechanics that is called wave mechanics to replace classical mechanics. And I think this is one very important mechanics that deals with all phenomena that involves electrons. And I said, as electrical engineers and as physicists and even chemists deal with electrons, as all modern technologies deal with electrons, it becomes very important to understand wave mechanics and how do we analyze the wave nature of particles or the wave nature of electrons, say in this case. So this wave mechanics is the same as what we call quantum mechanics. So quantum mechanics is another name for this wave mechanics or the mechanics that deals with waves. And again, just like Newton's second equation, there is a fundamental equation that governs the behavior of these waves. A fundamental equation like Newton's second equation. Newton's second equation is F, force, equals d by dt of the momentum, P. Okay, so that is Newton's second equation, as we talked about it at the beginning of this chapter, right? So that's the classical mechanics equation. So we should have a similar equation that tells us about the motion of an electron, okay, when we apply forces or a force. Okay, so what's this equation? Here is the equation, and this equation is credited to a German scientist called Schrödinger. So it's called Schrödinger's equation. It's just like Newton's second law. Okay, this Schrödinger equation relates the mass of the particle, the motion of the particle, and the force. How does it relate the force? Through the potential energy. Remember also when we were revising, we said you can always have a scalar function, which we call the potential function or the potential energy, right? And this function relates to a force, and this force is the conservative force. So if we take the force and get the potential of that force, then we can use it in this Schrödinger equation. In one dimension, the Schrödinger equation takes this form: minus h bar squared, the reduced Planck's constant, over 2m, the mass, partial derivative of a function, capital psi, delta x squared, plus u of x, capital psi, I is the imaginary number, okay? So it is an imaginary number, and we know that if we want wave behavior, we always have imaginary numbers to get exponentials, and then the exponentials give us cosine sine or sinusoidal waves. So that's I is the signature of getting waves. IH bar delta capital psi by delta t. So this psi is what we solve for, just like we solve for the position of the particle r at any time, to figure out, the motion of the particle. So this psi is called the wave displacement or the wave function. So we solve, here is the force or the potential of the force that is applied. Here is the mass of the particle on which we apply the force. And then we solve this partial differential equation in one dimension, x, and as a function of time also t, and we get a wave function. This psi is a wave function. Now, in itself, just as an psi, it doesn't have much of a meaning, physical meaning. Okay? However, when we multiply it by its complex conjugate, a complex conjugate in any function can be produced from the function by changing I into minus I. So this is how you get your complex conjugate. If you remember your math, you change I into minus I in a function, and then you get a complex conjugate of the function. And the complex conjugate of the function psi is what we call psi star. So psi star is a complex conjugate of psi. So if we multiply a function and its complex conjugate, then it has a physical meaning. So if this function is multiplied by its complex conjugate, then it has a physical meaning. And just as we solve Newton's second equation in classical dynamics to get the position of the particle, here, this product, the complex conjugate of the wave function psi and psi, gives us the probability per unit length. And if we're talking about 3 dimensions, it will be probability per unit volume of finding the particle at a certain instant in time, okay, at a given position. So it gives you the probability per unit length of finding the particle in certain position or certain space. So it actually tells you about the location of the particle. So it's just like R, the position of the particle in classical mechanics. But the difference is, this is a probability function. It's not an exact position. We do not claim that we know exactly the position. We know a probability. We have a probability of finding the particle in different places in space or in different spatial locations. So this psi, when it's multiplied by its complex conjugate psi that we find here, it is physically meaningful. It gives us the position of the particle or the probability of finding the particle. Okay, so I think we can take about 5 minutes break, and then we come back and try to finish